Good afternoon and welcome again to Environmental Geology. We're moving right along this semester, getting through our material. We're going to now start with Lecture 9 in the class, and we're going to actually cover two topics today, only one of which is in that book, in your textbook, the Primus book. And so the first topic will be on floods, and this is Chapter 12 for Abbott. However, the second topic we'll go into and talk about coastlines. There are no chapters at all, no material in that book. You're only going to get lecture material. So take real good care today to record just those lecture notes, okay? Try to catch everything that is on the screen. I'll try to keep it going as slow as possible. All right, floods is the first topic. All right, floods. And I thought I'd show this diagram, the schematic of the water cycle or hydrologic cycle. Again, I'm not going to go through the whole cycle. I just want to point out that, of course, within the cycle, that portion of the water that hits the surface of the earth, or that portion that already hit in the form of snow that melts, that runs off the surface of the land, that runoff portion, we refer to as surface runoff. This is the stream system, the rivers and the streams. And once in a while, that amount of runoff gets really high. And, of course, we refer to this as floods. What is interesting when you look at this diagram, though, and they try to break down where some of this water is in terms of percents, we notice that a lot of water, of course, is in the oceans, and that portion of the hydrologic cycle that's within lakes and streams is extremely small. But that small part, when it starts cranking up in a flood system, can be very, very hazardous. And so we're going to look at some of the things, some of the concepts and terms involved with streams, stream conditions, and what we record and measure and evaluate streams and floods with, and some of the things that we do with that before we move into the coastal area, some of the hazards associated with coastlines. And I want to use this slide to introduce two terms, two phrases. This kind of 3D block diagram is showing where as water hits the surface of the earth, that part that does not evaporate or percolate back into the ground runs off. And, of course, under gravity, it's going to flow to the lowest areas. And, of course, the surface of the earth is very irregular. And it's those low spots that the water is going to want to concentrate to. And so little by little, we have small little tributaries. The collecting system of a stream are referred to as the tributaries. Okay, the collecting system are the tributaries. And those small tributaries coalesce and become larger and larger and larger downstream till they hit the main trunk of that river system and eventually then distribute the water into a lake or into the oceans in the form of a delta. Now, the water that hits the surface of the earth, we can also look at it in terms of a regional concept of what we define as the drainage basin. Anywhere on which the water hits the surface of the earth and accumulates within this basin or within this region is referred to as a drainage basin. And they've got kind of two drainage basins shown in this block diagram, one on the right, one on the left. So there's kind of a boundary, a topographic elevational boundary between the two where water flows one way or flows another way. So depending on let's say on the stream that you want to talk about, individual streams can have their own drainage basins. Big Creek and Hayes have. The Arkansas River can. The Ohio River can. But those rivers can coalesce into one bigger system like the Mississippi River and have its own individual drainage basin. So we can talk about small little divides between small drainage basins or the great big ones like continental drainage basins, those that drain to the Gulf of Mexico, those that drain to the Pacific Ocean, or those that drain to the Atlantic Ocean, at least in the United States. So tributaries and the drainage basin. And this cartoon, or kind of from your text, shows us the Mississippi River's drainage basin in kind of the darker green area. And of course that drainage basin is not just the Mississippi River, it encompasses a lot of rivers. So all small ones that coalesce into bigger and bigger ones. But it's really a large area, removing a lot of sand, silt, clay, mud, organics, carrying that with that water off of the land. And of course most of it is dumped down here in Louisiana and the Mississippi Delta. All right? But what goes on in this system? What are some of the the functions that we're concerned about in terms of geohazards and how do we kind of work our way recording this information. Well, here's one kind of characteristic you're concerned about as a hydrogeologist, or excuse me, a hydrologist. A hydrogeologist studies groundwater. A hydrologist studies the surface water conditions. And one other concept or process we're interested in is called the stream gradient. And that's basically the steepness of the stream. How steep is the slope of the land? So up here in our diagram, if we would consider, a very steep drop in elevation, you have a lot of waterfalls and rapids, that's a high or steep stream gradient. As you get further and further away from the mountain systems and the land becomes more level and flatter towards the oceans in most places, like in the central U.S. with the Mississippi Drainage Basin, it's very, very low slope, a low stream gradient. Now, water is going to flow differently depending upon the stream gradient, how turbulent it becomes. And of course, as you go downstream, if we go back to this slide here, okay, as these tributaries grow and grow, the volume of water down all the way to the Mississippi is going to be carrying a great deal of water. We'll define that later on as discharge, what that volume of water is. So it's a bigger volume, and even though it's a flatter ground, that river is going to be carrying a lot of sediment and a lot of water, and it's going to flow differently. And that will then affect how it creates its own environment in terms of flooding and so on. So the stream gradient is a very important parameter that we look at. On the bottom of the picture, we kind of look at how the stream moves the water. Usually in the higher elevations, the streams tend to be a little bit straighter, where the gradients are more steep. And as you get down to lower gradients, the water tends to meander and zigzag back and forth. Now, part of that has to do with the way in which water flows internally in sort of a helical fashion as it moves down the channel. But also, that meandering pattern is created by the erosional capability of the stream to move the water, erode the banks of the stream, deposit sediment within its own system before it dumps it into the ocean. So that meandering pattern is partly hydraulic in terms of the physics, but also partly erosional as to how that large amount of water in these lower stream gradients distributes that water and brings it to the coastline. Meanders, of course, then we could say reduces the gradient and slows the water flow because it's meandering over a much lower gradient back and forth rather than just going straight from one elevation to another, as this cartoon is trying to show between the right and the left-hand side of it. Now, eventually, the water gets to a certain point. The streams either get to an ocean or they'll get to a lake. So we need to define another parameter. It's called base level. And here's the definition. Now, base level is defined as the elevation at which a stream enters a large body of water. Now, this could be a lake. It doesn't have to be a large lake, but usually it's the ocean, a sea or an ocean, where this enters. But along the way, it could pass into a lake. Now, we refer to the ocean level as the ultimate base level. Sea level is the ultimate base level. Along the way, if it drops into a lake, or even behind a dam that we build, we get a little localized base level. And the conditions of that stream change when you do that. If it's dumping material into a lake or we build a dam, we're changing the velocity of that stream. We're changing the mechanics of it. When it gets to the ocean, that's the end point. So the elevation at which a stream enters a large body of water or a lake. I'll leave that up there so you get all the notes down. Okay, now let's define one of these other parameters I mentioned earlier, discharge, the amount of water that the stream is carrying per unit time. So discharge, you need some parameters about that stream. You need the width of the stream, you need the depth of that stream, and how fast it's flowing, the velocity. This is how we calculate it, a little math kind of calculation. So the definition is in red, the volume of water that passes a given point over a given time. And I've given you one expression of that as far as units are concerned, cubic meters per second. Now, how that's represented depends upon the stream and in what country we're working with, but this is kind of the metric system here. cubic meters per second, and that's discharge. Now, all across the United States, there's a federal organization called the USGS, the United States Geological Survey. And they've set up for a long time, and even more, and much more recently, lots of little gauges to measure the velocity of the stream, and they'll calculate the width and the depths and stuff, and they have these discharge values today that can be measured instantaneously and seen instantaneously. I've got a number of pictures up here of different kinds of gauging stations that are around the country. In this case, this one's even collecting maybe some of the sediment to measure the load value. And so some of these are fancier than others, some are older, but right here in Kansas we have lots of them, and I'll show you a couple pictures of some of these in a bit. So we want to measure those discharge values. This is an image figure from Abbott's chapter on floods, and of course the way they show this is the thicker the black line, the larger the volume of discharge and the faster it is. And it kind of depicts that idea I was telling you that, you know, as you move downstream, discharge values go up because there are more and more streams coalescing to carry more and more stuff. So if you get an increase of rainfall in one area, this is going to increase, and that's when we get our flooding. So we're monitoring this 24 hours a day. Discharge. In western Kansas, in Trego County, we go by this spot on one of our field trips, along the Smoky Hill River. The river's down here in the bottom right. You can hardly see any water in there. It's pretty dry. But there's this gauging station there. And if you look at it real closely, you'll notice it's got a solar-powered battery system, and it's got this antenna this antenna is beaming up information to a satellite, which goes to a USGS site, which goes to a state site, and you can log on to a website and actually see this data in time, anywhere you want. I'll show you the map later on. I'll show you some examples of how that works, some of the kind of images. So there's a lot of data that's being recorded and kept, and we'll look at that a little bit later. Here's another thing we want to look at when hydrologists evaluate streams, what's called the recurrence interval. How often do streams flood? Okay, this happens to be a chart of the Red River in Fargo, North Dakota, and you can see from different dates and times of, when the floods occurred, and they plot them up in terms of what the peak discharge was. In a particular, this is cubic feet per second in this case. And then, of course, when. And you'll notice that a lot of the plots are way down here in the lower end. Not huge. These are the biggest floods. Way up here, the discharge was tremendous in 1997. But most of them are down here. All right? And so this is referred to as a flood frequency curve. And somebody is interested in that curve. Somebody wants to know, how often does a stream flood? And a lot of that has to do with saying, okay, this particular stream system, knowing about its drainage basin, knowing about the weather and the rainfall, is going to flood every 25 years, every 30 years, every 50 years, every 100 years, because when we build along a river system, we want to know that to get ourselves away from it, because something is tied to that, to these frequency curves. There's a certain group of business people who look at that, and engineers and so on. All right? Now, of course, no flood has a 100% chance of occurring. No river has a 100% chance of occurring all the time. And we know that a stream's not going to flood constantly. All right? But we want to look at those frequency curves, and I'll come back to that, and we'll see if you can think of who would be interested in that. All right, another functionality of stream systems is to how they erode, how they kind of change their shape, and how they kind of help define the topography that they work over. All right? Now, in the little cartoons, as we go through the sequence, in the top picture first, because of a subtle, slight meander to the stream, a kind of low sinuosity to it, the stream wants to go straight ahead. The mass and force of the water wants to go kind of in a straight line, although in 3D it's kind of moving down the stream in a spiral, helical fashion. But the force is going to be on the outside bend. You're going to get erosion out there, just the physical force of that water. So on the inside of a bend, it's going to be, more deposition taking place because the velocity is slowing down. The force of the water is not hitting there. So remember this. Erosion on the outside, deposition on the inside. Erosion on the outside, deposition on the inside. So little by little, you can actually see the shape of the channel change. You can see it become more of a meander, more snaky, more winding back and forth. And look what's happening to this house in this one particular spot. So in time, what's going to happen? There's a hazard here. This house can be undercut and a structure will collapse. So they have a choice. They can move or they can attempt to build some kind of protective barrier on the outside to reduce the rate of that erosion. And that's affecting the mechanics of the stream. So erosion on the outside, deposition on the inside. Another thing can happen in this picture is that we can see that there's kind of again, a low sinuosity stream, but it's kind of in a confined valley in this case. And little by little, that outside bend is going to undercut the cliffs or the terraces on either side and continue to create a meander across that lower floodplain. And sometimes the meanders get so snaky that they'll actually cut themselves off. The stream will make such a tight bend it comes around in a narrow neck and erodes itself off and goes down that lower elevation quicker and isolates, as you can see in the bottom picture, an old bend, an old curve on that stream system. So they're constantly shifting, they're constantly changing. They deposit sediments and they erode material. So they're a very dynamic type of process. Constantly changing. Here's a real photograph of the Sweetwater area in Wyoming, and you can see an old meander, kind of a cutoff. There's still kind of water. There's a little bit of vegetation building in. Here's a real faint one. You can just barely pick up an old cut-off meander, as we call them. A lot of times these eventually get filled in with vegetation and silt in during floods. But that's the way the system works. And so if we're going to live along these areas, you know, where do you want to place your house? Where do you want to place protective barriers? I throw this one last shot up here for the heck of it. Again, it's similar to the other ideas of the meandering stream, but what kind of material do we get in here? Another thing to be concerned about is the cross-sectional view of the layers, where the gravels are, where the sands are, where the silts are. As we maybe drill wells into those alluvial deposits, the unconsolidated sands and gravels, and try to pull water out of them, and how that affects it, or where you might get an overpressurized zone to cause something else to happen, as we'll see later on. We kind of looked at it a little bit earlier. All right, what about some past floods? I'm going to show you a couple examples of some pretty wild floods that are not necessarily directly the major river system kind of floods we're thinking of today, like the Mississippi flooding or the Kansas River flooding and the Missouri. This is an area in Washington State, in eastern Washington State. They kind of nicknamed the Scablands. About 10,000 years ago, 7,000 to 10,000 years ago, as the glaciers were retreating back into Canada, one of the lobes of ice blocked off some water flow from another region of another front of ice melting and created kind of an ice dam called Lake Missoula. And it blocked up this huge lake. Well, eventually the lake level got so high that it started cutting through the edge of the ice in the land, and all of a sudden the whole thing caved in and gave way, and a huge, huge lake just spread out and flooded into eastern part of Washington. And I mean, we're talking 5-10 miles wide in some places, river systems, with a huge amount of velocity moving very quickly. You think Niagara Falls had some great waterfalls today. The waterfalls at the edge of these little cliffs right in here, then they're all pretty much dried up. There's fishing lakes now at the bottom of them that were just huge and tremendous at that time. Kind of really dwarfs our modern day Niagara Falls. So that's one example. But it's kind of glacial related in a way, not so much rain per se. Here's that old map. The ice dam developed here, and this huge lake formed, then erosion cut through, broke that off, and this huge amount of water just completely flushed out and quickly eroded and changed the topography, and now it's all dried up. It's more of a desert area in this part of Washington. Here's one you may not have heard of. About 7,600 years ago, sea level was rising at a fairly good rate because, again, on a worldly scale, the glaciers were melting and retreating. And so sea level was going up. And if you look at a map of the ocean's connection to the Mediterranean Sea and the Mediterranean Sea connection to the Black Sea, there were some little inlets in here, and for a long time, the level of the water in the Black Sea was way down. Way, way down. Okay? But when sea level rose so quickly, and it inundated and caused the level of the water in the Mediterranean Sea to go up, it actually eroded and cut through the Dardanelles right in here in the Bosporus Strait and began to create this huge, very rapid flood about 7,600 years ago when those glaciers melted. And at that time, we're talking about water moving in very quickly. People had to really move now. They weren't waiting for months. This was going on very, very quickly. And so a lot of people in this region of the world got displaced dramatically. It was a pretty scary event, I'm sure, at that time. So those, again, glacier related. But what about the recent ones? Here's a shot of the 1993 flood in the Mississippi River. Some of you from eastern Kansas would probably, and Missouri and Iowa and those regions remember more about this all the way down the Mississippi. It was quite a wet year. Even here in Hays, Kansas, we had trouble with it. And you can see a lot of the floodplain out here that's completely submerged, a lot of homes underwater, a lot of damage. Here was a kind of a flood, more of a mixture of water and mud that came out in the Rocky Mountains north of Denver. It's called Big Thompson Canyon. Tremendous rains and a very rapid buildup of water came blowing down that canyon, cut out the outside banks and undercut a lot of homes. The wall of water and the rock with it, and homes coming along down with it, were moving very fast. There were some people who got trapped even on the highways, could not drive fast enough to get out of the way of it. So some floods may be a little slower in their growth and some extremely fast. And you always hear about it on the news. You watch the Weather Channel, you can talk about, people don't drive into the low areas during flash floods. And then you always hear the story. Somebody does, and their vehicle's moved. I think this is an interesting thing, kind of a little bit of mechanics, the physics of it doesn't take too much water. Maybe you got a big old SUV or a bus or a truck or something, you go through 1 foot of water that's moving, only 500 pounds of lateral force, but just double the depth of that water and it triples the force. Then you can begin to have problems, and this always happens. So kind of a preventive measure of geohazards, just stay away from any kind of low areas during flash flood times. Listen to what they tell you. It doesn't look like it sometimes, but you can easily get caught up in this stuff. Some other pictures, more flooding, obviously buildings moving. I think this particular scene here of Cassis being eroded out from a cemetery, from the hydraulic force, and all of a sudden you see all these caskets being floating down the streams. You want to recover that. So a lot of things can happen. Here's one in eastern Kansas that maybe some of the eastern Kansas people might know about, Tuttle Creek near Manhattan, Kansas. This big reservoir, 93, really got flooded. And this spillway on one side of the lake, this is that big earthen dam, was really flooded over. Tremendous amount of water cutting down here, and the erosion that went on in these rock layers below the dam was phenomenal. Here's a shot from the dam, and once the water's receded, all kinds of geologists love this. And fossil collectors, they could go in and find all these really neat new exposed, fossils in the river bottom. They've since kind of really tried to protect that more, but down in here at that time, this was really quite spectacular kind of stuff at that flood. Well, here's one of those people very interested in flooding and frequency curves and all that is insurance agents. If you take a look at your insurance policies on flood insurance, look at that rider on there and just see how that fits into your area. Right here at Fort Hays State Campus, we were concerned about Tomatic Hall at one time. Before they built that building over there, at the last minute they realized they were supposed to bring in 4 more feet of fill. They were almost getting ready to set pilings and everything, and so they went in there real quickly and got that up because they were on a floodplain of Big Creek. Even though Big Creek doesn't flood that much, we had a biggie in 1950s, late 50s, and had a lot of disastrous things happen. Some people died from it, and there's a bypass around our campus now because of that. That's a man-made levee out there. I mean, the creek kind of meanders through the campus, but we kind of funnel that water off in different directions. So, there's a lot of damage. Anytime there's damage to structures, insurance companies, whether it's hail, hurricanes, floods, it's all part of it. Of course, we're concerned about all the others. Here's some of these. If you get on the website, and I'll give you the website address in a bit, you can see in time some of these rain gauge databases. They get on a screen. This is just a screen copy from the USGS site. This happens to be Big Creek, just last fall, September 10th. And here's the real low level of water. And all of a sudden, bam, we got 6 inches of precipitation. This is a precipitation chart in 43 hours within that little drainage basin and how it affected our area. Waterfalls in another drainage basin. It doesn't concern Big Creek. All right. Here's one on how quickly the level of the water rose. The red line is the flood stage line, 18 feet above its normal level. So this is gauge height, and we popped up it just a little bit. Not for long. We didn't go over our levee, but we went above the flood stage, and that's a warning signal. You can check them out. Got 10. Went up. The river went up 10.16 feet in a very short time period right in here. Just in that, you can see from September 11, about a half a day, that water level rose and moved on downstream. Here's an interesting table they have up there on how much water went by in terms of volume again. Not so much the discharge rate, but how much water. Now here we have the discharge rate of 364 million gallons in 4 hours. You don't have to memorize that number. But, 1 billion gallons for the storm, by the time it was all done, 1 billion gallons somebody figured out could supply the city of Hays with water up until February 2005, if you could catch it and store it. So, some people try to do this to say we need that water. Otherwise, it's going on down the stream and heading towards the ocean. So you can get at these. If you get on a website, the USGS Water Resources site, this is for the state of Kansas. You can get on any state. And all these little dots on the screen, you can click on a particular stream, it'll bring up those charts. And you can calculate them. So why don't you, if you want, you can write down this website, http://ks.water.usgs.gov/ and you get on there and you'll get to that website I just showed you. And once you're there, there's even more unbelievable links to more and more water data, to the Kansas water offices and so on. And every state has this. Some are more well-developed than others, but it's a big kind of an alliance to keep a track of what's going on with our floods. It's data. It's a database that we need for analysis and how to plan for these things and how to work around them. So ks.water.usgs.gov. I won't go to it right now, but you can check it out. All right, let's jump back to some other ideas. Now, once humans get involved in the streams, we have dammed up rivers for a variety of reasons. TVA project, of course, for electricity, to have hydroelectric power. And we've got some big dams out west, like Glen Canyon Dam and Hoover Dam. Hoover provides, practically all the electricity for Las Vegas. Okay? But when you dam up a river, you change the mechanics of that river, as I said. You're changing how things happen in terms of base levels. So I want you to remember a couple other things here. Besides the fact that dams are built to store water, we can have electrical power, we can store water, you have recreation like fishing, skiing, boating, picnicking, whatever, along those, migratory birds. But there's a downside too. You can have evaporation, loss of water, or it can soak into very porous sandstones like out in the Navajo sandstone out west. But when you build the dam, you slow that water down, and little by little, the sediments coming in begin to build up at the bottom of that reservoir. And we're checking them every month out there, the reservoirs. How long before they fill up becomes a great big sand body, and you got a real fancy concrete waterfall. 50 years, 100 years? When will Vegas run out of its electrical power from there? We have to be concerned about that because we've messed with that mechanics. The water that you funnel through the dam to make if you do hydroelectric power, is going to be colder water, and you force it out at a much faster rate, and so you get erosion below the dam, and that's going to affect anybody below that dam. The erosion rates are going up, and the ecosystem of colder water is changing the biology of it before it eventually makes it to the sea. If it does, as we mess around with the mechanics of streams. So one thing to look at, here's an example, the 1925, they call it the Malibu Canyon Dam. Well, they put the dam up nice and narrow, but so much sand and silt came down, 13 years, it became a nice concrete waterfall. So there's no body of water behind it anymore, it's all sand. Now you have a choice, you could dig it out, That costs a lot of money. And most of them aren't doing that at all. I don't know of hardly any, to tell you the truth. So, it's something to think about as we play with river systems and work with them. All right, what about big cities, urban sprawl, urban effects? When you build a parking lot or highways or houses, you're essentially covering up the surface of the earth with an impermeable layer. You reduce the soakability, the infiltration rate of water to percolate back into the groundwater system, and you increase runoff. So urbanization increases runoff. Now, where does that go? It goes into the sewer systems, it goes into the little canals and rivulets or whatever you got. The flooding rates are going to go up, particularly in certain parts of town where that water gets funneled. And you could pick any city like that in the country and pick spots within your own hometown to see that. The fact that you actually put the buildings there occupy space or volume that water could fill when it does flood. And so really you're kind of raising the potential new higher flood level the next time around by building more buildings on a floodplain. And of course, don't forget that as water runs off the surface of the earth and goes into your sewer lines, it's bringing, sand, silt, mud, trash, and it begins to fill those sewers in, and so the volume of water the sewer can carry becomes less. Sometimes it flushes out, sometimes it doesn't. So any kind of activity that we do is changing this process, and we have to learn to live with it. What happens with these urban effects. Okay? So urbanization increases runoff by a variety of ways, kind of indicated in the rest of this. But the key thing to remember is that urbanization is going to increase runoff. That's kind of why I highlighted it in blue for you. A cartoon, again from your text, by kind of depicting this building of houses real close to the stream. If you add volume, that volume that building occupies means the water's got to go elsewhere, and especially if you seal it up. Certainly, if the water fills in the house, then that's a different story, but it depends on how well they are. I saw some of these in the Mediterranean, one of the housing flood problems that was going on in Venice. Really wild story about that. So, what do we do about it? What are some things we can do to mitigate flooding problems? All right, I'm going to go through a list of things now for the mitigation of flooding. Most of these involve urban city areas. As you can see in this particular shot, the span of bridges, that a lot of the highway part is, it's underwater. Okay, so what are some things you could do? Well, right here on campus, because of the floods, we built an earthen levee to bypass the campus. Around the west side of the campus, they take that meander where it cuts more into the campus, and they funnel the water around the western side to take most of the water out. Some of the water still goes through campus, so by splitting it, it's again reducing, giving more volume space for the water to go to, and that building a much high enough levee so if it does flood, to try to keep that out of the campus. And once in a while, that doesn't work. We came close to flooding in 1993. Another thing you can do is to try to create special channelized, very straight cutoff zones from one meander to the other, concrete or earthen, to say, let's get the water from one end of the town to the other end of the town as soon as possible, and build it big enough to take that volume away from our city. And of course, we'll see that that can be a problem later on. But when there's money involved, we want to do that. Loss of life. You can build great big flood walls, whether they're earthen, rock, concrete, steel. Put these great big floodgates in there if you need to get to the river for whatever reason. I know in Cape Girardeau, Missouri, is a really interesting flood wall with this great big gate that'll move in and out when the Mississippi's flooding. And it helps get that water right past Cape Girardeau downstream to other people, other communities. Or you can try this. You can say, hey, look, you've been flooding and flooding and flooding. And this has cost everybody lots and lots of money. A lot of damage, a lot of loss of life. So you pass law and say you can't live there anymore. You can't build there anymore. So you can create flood zones, kind of a legal approach. There's something related to this legal end of it that's really beginning to develop a better understanding of a flood and how it moves down and how to monitor it before it, during it, and after it. And what it involves are a bunch of in-time remote sensing images from satellites and building those images as database with past information and where highways are in a kind of an integrative thing through GIS, Geographic Information Systems. And then have an evaluation plan they refer to as risk assessment. It's kind of fine-tuning how we used to do it just visually, is what it is. It's quicker, and it's helping a lot of areas of the country to deal with this. GIS and remote sensing. But whatever you do, not so much the last one, but any of these things to get the water away from your community, of course, is going to increase the velocity and the volume of water downstream from you. And you're displacing the problem. You're moving it to somebody downstream, and it's their problem now. Okay? It's their problem. So what about some other things we might be able to do along the streams or maybe in the countryside? If we move it out downstream where there's smaller communities or farm areas, what can they do to maybe kind of keep water out of the streams to avoid any kind of flooding in their local areas? One way would be to build some retention ponds in certain areas. Build a little earthen dam, let the rainwater collect in there, make a bass pond out of it, and hold that water back. Or if you get into the terracing and contour plowing, to again hold that water back on the land to keep it from going straight into the river system and silting it over. Or more vegetation, strip planting, alternating crops, and keep the mulch on the land so that the soil isn't eroded very quickly and boom goes into the river and floods. So these are some more things you could maybe do near a city, but more so out in the countryside area to work with mitigation. Kind of a cartoon picture of, I think you can kind of visualize it. If you've got water coming in, it's going to flood and you're on the floodplain with your farm. Well, if you build a retaining pond out here, then that can prevent that. If it's local. Depends on where the water's falling. Don't forget about the drainage basin business. Where that water lands on becomes what part of the system. If there's an upstream flood from a bigger city, they're still going to get flooded. And maybe too much water might even undercut and erode their retention pond too. So a lot of things can happen. So I know like here in Hayes we built that levee. I have a cartoon of this business of building artificial levees. And you get the water out of your town very quickly, but what is it doing? It's moving it downstream. And of course, the greater the water is behind that levee, the higher you get that levee, the greater the pressure is on that levee. There's water pressure pushing outwards on the sides. There's a lot of pressure underneath within the sediments going on. And I know with some levees you can actually get the pressurization to come through the bottom of the channel and squeeze on out and have sand squeeze up through. They call that piping, or little sand volcanoes, and spread out and bring water into the floodplain. Or maybe the water pressure can begin to cause fracture patterns and slumping, or it goes over the top if it's real windy. So you're always seeing them, put more bags on top. So a variety of things can happen, whatever we do, as you're always shifting where the danger zones are. I think I've got some pictures of some sand boils from previous times. These are kind of maybe more earthquake related, but you can get these same kind of sand boils along the margins of earthen levees. Now if that's going out into your house or your driveway or your road or your backyard, because you got that levee, well then you have a problem you have to clean up too. So it's still a hazard. If you break through the levee, then you're going to get a lot more. Now sometimes these breaks are natural like this and cut through. Sometimes they're not. Once in a blue moon, we had an interesting case, I think, back in the 1993 flood where somebody got mad at somebody and dynamited one. And that water went off into another community and some people got killed from it. So things can happen. Anyway, that's it on the flooding chapter. I want to move on now to coastlines. We'll look at coastal situations and some of the coastal dynamics here. There's no text chapter, remember now, to read about this, so take good notes on this part, all right, coastal areas. Let's just take a look at some pictures of where sediment is brought to the coastline. We've looked at floods, we've looked at rivers of discharge. These are some really spectacular shots. This is in northern Russia, the Lena River Delta. Kind of a very spectacular, pretty infrared image of that area. But this is where that sediment is distributed and things are brought to the coastline and moved around. And that coastal dynamic has a major effect on how we live along coastlines. Here in the corner, kind of the Gold Coast of Africa, in the country of Niger, the Niger River coming down, a really kind of unique shaped kind of pattern river. In Vietnam, the Mekong River Delta, and you can actually see some of that sediment being brought in. Look at the Mississippi, tremendous amount of load discharge with the Mississippi River. That shape is controlled by the river. And look at all that sediment being brought out. Pretty spectacular kinds of potential flooding, especially today as we keep channelizing a lot of stuff away from the mainland. The Rio Grande River, kind of more smoothed out, but very, very populated, high potential for floods. And here's your barrier islands. Maybe some of you Kansas people are going down to Padre Island over spring break that's coming up. Coastal dynamics. So, most sand that we find in our beaches and our coastlines are brought there by river systems. And they're deposited by the delta system. Okay? This happens to be the Nile Delta. Of course, in Egypt, this is the Mediterranean. This is the little delta symbol, where we kind of get the symbol delta from the Nile shape. Okay? But one of the things that's interesting about human involvement with the Nile River is that the Egyptians had the Russians build a dam for them called the Aswan Dam, and Lake Nasser has piled up behind it. So a lot of the annual sediment that would come down the Nile River and flood this area has been reduced. And so because the amount of natural flooding sedimentation that takes place on the delta annually, there's no more deposition. There's no more buildup. But there's still continual sinking and subsidence by that river system. And so because of it, the waves are beginning to erode at a faster rate than the river can bring sediment to that coastline. And all those great big high resorts and condominiums they built, especially the ones closest to the ocean, they had to abandon them. They're being undercut by wave action because there's no sediment. So they're having beachfront loss because they built a dam. It's a displaced problem. When we mix with the mechanics, it has caused problems. Here's the Aswan Dams built way back down here on the Nile, and this is the lake back in here, and there's that actual dam. This is silting in. A lot of things have changed. I could go into about, biological things as well. So we're getting the same kind of thing in the Mississippi River. Okay, same thing. Here's the Mississippi Delta, and we have changed that system. We've channelized the river, we've put locks on the river, and we want to get the water away from our cities. We don't want the floods. But because of that, the Mississippi River is sinking, kind of subsidence very slowly because of we don't have the sediment flooding out there annually. So you can go along a lot of places on the Mississippi River and you're actually below the level of the river. In restaurants and houses and schools and whatever, like in New Orleans and Baton Rouge, and it's continuing. And of course, along the coastline out here, if it's happening, sinking faster than its natural buildup and being sustained, any kind of oceanic hurricane surges are bringing salt water in, and they're actually losing farmland very slowly. And so it's a hazard. It's become a hazard in this process. So let's kind of take a look at some of these coastal processes, the dynamics of a coastline. Okay, all the rivers bring the sediment down. Here's a really beautiful picture of one of the barrier islands in North Carolina. They call it the Outer Banks. A bunch of barrier islands, and this is the Atlantic Ocean. This is a great big kind of estuarine type bay behind it. And the mainland you can't see. So it's kind of a protective barrier to the mainland. But things change constantly here. And it's a beautiful place to live. But things move. And a lot of money's involved, especially when the big storms occur. Here we have these nice, beautiful string-lined beaches along this part of the Outer Banks, and kind of a strange little extension, a really big extension of sand sticking out right at the tip of this thing. This is the thickest part of the island. This is Cape Hatteras, right here. And Cape Hatteras has a lot of history to it I could go into, but this long extension of the sand, as if the beach is spitting sand out into the ocean. They came up with a phrase for this extension of sand. Call it a spit. Pretty straightforward. But that's because sand is being moved by currents. So I kind of want to look at some of that dynamic movement along the coastline, because if you live there and you move the sand, you move your beach. Your beach could be somebody else's beach someday, or you'll get their beach by this continual changes. So one of the things, of course, that shifts sand around is the continual breaking of the surf. Sand is washed up into the swash zone on the beach, and that sand goes back down in the ocean by gravity. So if the wave is hitting the land at an angle, the sand grain goes up on an angle, but it goes straight back down by gravity. So sand shifts along that swash zone just by that continual wave action. And of course then out here, it does the same thing a little bit, and so you get the same kind of shifting of sands here, up and down the beach line. So our goal is to try to keep the sand by our beach and build all kinds of structures. Or if we get big storms with big waves, we don't want it moving, so we put big concrete walls with special geometric shapes. We put a lot of rock out there to reduce the energy. So it's, big wave, it's going to maybe move a bigger piece, but certainly move sand quite easily. So part of that process of this destruction of headlands, movement of sand along the embayments, is caused by what we call wave refraction. Wave refraction is as the wave fronts approach the land. The part of the wave front that's coming in, that's in the shallowest water first, in other words, if these wave fronts come in at an angle to the land, the shallower part slows down. The deeper water part's still moving. So it's the change in speed that causes the wave front to curve. The fancy word for curving is refracting. So we say the wave refracts and curves around the coastline and then shoves that sand up on the beach. It comes back down, and the currents are constantly shifting up and down by those longshore currents and the wave refraction process to smooth out a coastline, to spread the sand the rivers brought to our coastlines around. So this is a day-to-day process. It's a real slow, continual process. Every wave comes in, it swashes up on the beach, the grains go back down, up on the beach. So the sand is moving right on the beach itself or just offshore. The sand that moves is called drift, the currents moving it. So longshore drift is the stuff moving. Longshore currents, of course, are the transport mechanism. Now, if you've ever been to a beach, maybe you haven't, but you walk out into the water, it's kind of shallow, and as you do that, of course, just stand there and let the waves go past you up onto the shore, up to your knees maybe, and then stay there, and the water, of course, goes back in the ocean. You can feel the water dragging against your legs. That's called the undertow. Now, the steeper the beach, the bigger the wave, the stronger the undertow. Now, if it's big enough and you're not too big, it can clip your legs out from under you and drag you out, but it's only going to drag you a little ways. It's not going to drag you way out to sea. It's something else that can pull you out to sea. It's called a rip current. Now remember when the waves come in and they crash? The wave crests and it breaks and it smashes in? As it smashes downward and curls over, it gouges a little funnel out, a little kind of trough parallel to the beach. And of course then it shoves all the sand and water up on the beach. It comes back down. Just try it one time. Walk out in the water and all of a sudden you'll dip down real quickly. You're hitting that trough. And then walk further out, you'll be right back up into shallower depth again. As you walk through that trough, well, these troughs are in all different kinds of shapes and positions along that shoreline. Now, a very special condition has to happen for that trough to create a rip current. The troughs have to be tilted towards each other such that the water that not only goes back in the ocean, but the water in trough funnels parallel to the beach in one direction. In this case, it's going towards the top right. Up here, it's coming back down to the bottom left. And where they meet, they don't shove back up on the beach. They go straight out in the ocean. Well, that mass of faster moving water is called a rip current. That's the one you have to watch out for because that'll take you way out offshore. Now the sediment it carries with it, which could be you, okay, is called the rip head. The current is the movement, the sediment stuff is the head. And so lifeguards in these areas will look for these things. Keep an eye on the mechanics of that, and they see that kind of brownish plume out there in the water, and then they'll announce it, or you'll see signs and shifting. Get out to California, just go up and down the beaches and see all the signs about rip currents and the warnings, besides the shark warnings and stuff. And everything else that's in the beach these days. You know, bad stuff. Okay. Here's another thing that affects the water level along our coastline called tides. Now we know that a lot of places on the planet have different kinds of levels of how high the tides get. Sometimes you have 2 daily high tides and 2 daily low tides. Some places it's 1. I'm not going to go into all of the mechanics behind how many we have, but the reason why we have them. The main reason why we have coastal tidal changes is due to the gravitational pull of the moon. It's the nearest celestial body, and it pulls on the Earth. It pulls the ocean upward. And of course, the Earth is also spinning on its axis. If you happen to take a basketball and spin it and put some water on it, what does the water want to do? Fly off, kind of get higher, so to speak. So the centrifugal force of the Earth, the gravitational pull of the moon, the asymmetric shapes of the coastal margins, the positions of the Earth, Sun, and Moon can change how high those tidal changes can be. And tides are moving water. They shift sands. In the case of the one on the left, they're called spring tides. Spring tides are the highest tides you can get. And they don't happen only in the spring. They happen when you align the sun and the moon's, of course, between the sun and the Earth, so you have double the gravitational pull, so to speak. It's not really double. You can do the physics, but you get an extra increase of gravitational pull, so you get a much higher pull of a high tide, okay? Now, in the picture on the right, the lowest low tides are called neap tides. And that's when the moon, the Earth, and the sun are in a perpendicular arrangement in space. Such the moon being the biggest one is going to pull the highest amount of water upward. The sun's over here. So somewhere in between we have our differences. So the highest high tides are the spring tides. And they can occur any time of the year. Whereas the lowest low tides are neap tides, and we have all our others in between. Kind of a shot of a coastline of a low tide moment. And of course, if you can get a higher tide, not too much later. So that tide maybe went up a few feet. The Great Lakes have a tide, maybe of 2 to 4 inches. But there are some coastlines, because of the configuration, the shape, when that water rises, it funnels. It can funnel. Like the open California coast and the open Gulf of Mexico coast, you might get 1, 2, 3 feet of tide changes daily. That's not that big. And if you live on the coastline, it's just like a daily report. It'll be in the papers. But here's a spot where you can really watch some big tidal changes. You want to watch 20 to 30 feet of daily changes. Go up to New Brunswick to Fundy Park. And as the water comes up this kind of conical shaped coastal area, it squeezes the same amount of water into a tinier and tinier spot. And coming up into these bays is just amazing. I could go off on a lot of stories about, the historical aspects of getting food out of that, but I don't have time for that. But the Bay of Fundy, here's kind of one of the low tide times. You can go out and hike around and pick things up and stuff. But then they have whistles or kind of sirens sometimes that go off in these wooden stair steps to get out of there on this steep cliff area. Once in a while they got to go out and try to rescue somebody. But that water coming in moves in pretty fast. You can see it coming, and before long it's 20, 30 feet above where it used to be. But the whole bay can empty out. You can walk across that whole big mud pile. I'll tell you the story. They used to go out there, put wooden poles in, put nets up at low tide, gill nets. And then the high tide comes in, fish get caught. Low tide, they go out and pull their laundry off the line and eat it. Okay? And that's how they could get food that way, because of taking care of the tide changes. So some of these tide changes are pretty big. Here's high tide and low tide. And here's the tide. This isn't extreme low tide. The tides are coming back in. So the leading front of the new tides coming in, we call the tidal bore. B-O-R-E. The tidal bore is when the high tide's coming back in. And it could be a 2-inch high, 4-inch high, or maybe even higher tide. Now this looks like a typical surf's up type of picture, doesn't it? of this mass of water coming in. Well, this guy's not surfing on a coastline. He's surfing in the Amazon River. The Amazon River is a tidally dominated delta, and in these airplane pictures in the top right and in the bottom part, this very nice funnel-shaped entrance to this river system. Not a lot of sediment, but a lot of water in the Amazon. But as that comes up along there and funnels up, this gets a really nice, good 3, 4, 5 foot tall tidal bore wall. The indigenous people living along the jungles in there, they can hear it coming as it comes blasting through the trees and the vegetation, especially the biggest spring tide ones. They're going to be the tallest. That noise, in their language, you might want to remember this if I threw it on the test for the heck of it. Porta Roca, in their language, means big roar. They yell that out and they probably run for high ground. Porta Rocas. So you can get some pretty massive walls of water moving in because of tides. Just depends on the conditions. Now, it's not the only place that people do extreme sports and surfing. This happens to be a place in France, one of the river systems, a tidal bore, that are out there that they take advantage of surfing because of tidal bore things coming. It's kind of wild. But here's the whopper. This is the one we're concerned about, hurricanes or cyclones. Okay, depends on what ocean area you're in. Some fabulous pictures we've seen lately. These are the big changes. These are ones that affect our coastline a lot, are very damaging. These are the threats that we really have to check out. Big time. We start plotting them up from all the way out here in the eastern part of the Atlantic. Storm cells even coming off the African desert, and where they go and where are they tracking to. This is a major thing. A lot of money's invested here. You can see a time thing of just the one last fall, Hurricane Isabel in 2003. When it was out to sea, it was a Hurricane 5, level 5. By the time it hit the coastline, it kind of slowed down to a 2. But imagine a 5 coming in and hitting that. Especially out here. Say a 5 came into New Orleans with that, the storm surge is going to come in and pushing salty water into that farmland. It's going to destroy everything. So we really have to be concerned of understanding these types of kind of geohazards, so to speak. So we plot them up, we map them, we fly out into the middle of the eye. Here's a shot from inside the eye wall, right down inside that hole, the eye wall. You can see right down to the sea and see the turbulence. It takes a lot of courage, and I think people who do this are, should be given a lot of credit to keep an eye on this stuff for us. The satellites now we have to really plot that. But here's some of that Isabel damage from the storm surge. Pardon my picking on this individual in the bottom left, but someone for fun decided to go out and check it out. And that's how people get killed. You get curious. I remember the big rain we had here last fall. A lot of people were out chasing around town, checking it out, and the cops were trying to tell everybody, go home, go home. It's normal, I guess, inquisitiveness. This gentleman's trying to, with this little rod here, he's trying to pump out a sewer because the sewer had backed up with silt. Why now? I mean, what good is it going to do at this point? I mean, things have already continued. So there's a lot of damage, and hurricanes we can't stop. But we can attempt to try to do other things to take care of our coastlines. Besides the water and the wind and the storm, we can get a lot of dust coming in. Other problems associated with that in regions. Here's Ocean City, Maryland, 1977. Big surge came in and really wiped out a lot of property, a lot of damage. Again, cost to everybody. So FEMA, the federal government, to help people out, the state agencies, and of course, insurance rates go up. It affects everybody else. Here are some of these huge blasts where beach sands just blasted over the backside of the beach into almost to the swamp. We call them washover fans, where the beaches are destroyed. Hurricanes really can move a lot of stuff and kind of wash that sand over onto the marshes and the swamps on the backside. This is pretty fresh. Little by little, vegetation will begin to cover that up. So what do we do about it? What about the mitigation? All right. I'm going to talk about some structures that we build. And I want you to remember the name of the structure and how it's built. One of the first types of structures we build is a feature that's attached to the land and it's built perpendicular to the shoreline. That's a key thing, perpendicular to shoreline for a groin. Okay? A groin is built perpendicular. Now it can be a solid wall, it can be impermeable, a variety of styles of those. But I want you to look at the mechanics of what happens when we do that. All of the wave crests are coming in at an angle. So because of longshore currents, the sand's going to move from up here and migrate down and pile up against that groin. Now, if you have a house here, you get a nice big beach. But because of wave refraction, which they didn't show too well in this picture, the wave energy curls around the backside of the groin on the downdrift side and erodes out that area. So if you had a house right here, it's gone. So who built the groin? You, the state, the city, the county, the federal government? And who is this person down here going to sue? You move to a coastline, you're going to hear a lot about this kind of stuff of whose land is it and the sand development and where we're going to get sand and how we move that because we build a structure to protect ourselves. You mess with the process, something else affects and gets displaced downstream somehow. Here we have kind of a little inlet. There's a special name for these two types of structures I'll get to in a bit, but deposition on the upside and more erosion down here. You can see that the shoreline's changed its width. We'll want to dredge this out, especially if we have a marina back here. Here's the one at Cape Hatteras, the old lighthouse along the coastline. They actually physically moved they couldn't do much more along the coastline, so they moved it a mile or a half a mile back. An old historical thing, but here's one of their groins they built. And it's kind of being eaten up, but deposition, erosion here. Things they did, slowed it down, but didn't stop it. Here's the second structure you need to remember. It's called a jetty. If you have an inlet that goes to some, again, a marina or waterway that's along the land, when you have two parallel types of structures at that inlet, it's called a jetty. And sometimes the jetties have double angle bends and all kinds of stuff because we study the average direction of the currents and the wave refraction on a yearly basis and try to, engineer that to fit that specific condition. Sometimes it works, sometimes it doesn't. But there's a lot of money. There's a little dredge you can see in here. They're dredging sand out. They'll put it on a barge. They'll take it over here, put it in a truck, and bring it back to the beach. A lot of people involved in shuffling that sand around. That means money. So it's part of the economy, but it's part of the process. All right, third feature, called a seawall. A seawall is built attached to the land and parallel to it. Here we have some land on the right. Here we have this wall of material, probably concrete, wood, and rocks. The cartoon in the bottom right-hand side, it depends on how good you are at building it, but the cartoon kind of shows you, I guess, an unsuccessful seawall where that high-rise structure got hit. But seawalls are attached and parallel, whereas breakwaters are parallel, but they're offshore. Now, they could be 10 feet offshore, a half a mile offshore. Depends. Here's one that's built kind of close to the shoreline with a groin attached to it so you could walk out on it. Sometimes people don't like those out in front of their houses. They think they're ugly. So they've developed some that are actually submerged, some specialized shapes. So some breakwaters are actually submerged. And it can become kind of a little fish crib offshore in a way. Sometimes the surfers love to build special shaped breakwaters to increase how the surf and the wave breaks to come into land, and use them in kind of contests and stuff. It creates a special geometry to that process. So whatever you do, you're changing where things are eroded and where they're deposited. This happens to be a cartoon about, well, when you build a breakwater, you'll get an increase of buildup of the sand there because you're protecting it from being hit. But you concentrate the wave somewhere else, and so you get an increase in erosion. So these people lose out, these people win. And it's a constant dynamic battle of nature, including humans, over their beachfront property. We've done things like build great big, plastic bags full of sand to protect that house. They put vegetation and kind of sand fences to keep the wind from blowing the sand around. It's like a snow fence. They'll bring sand in from one place and dredge it up and put it out here before the tourist season and bulldoze it out and build it up, or at low tides get out there and try to bulldoze it back up on the beach. When you live in a coastal area, you'll see a lot of activity about controlling that sand that nature's shifting around, because if we don't have the beach and the big storms come in, the hazards go up and the damage increases and affects everything in life. Now I'm going to show you this shot here for the heck of it. Wafflecrete is a company in Hays, Kansas. And we often think of them building concrete structures for houses and stuff like here on the bottom right. But they also build some coastal things. Things used for piers, groins, whatever, for those coastal communities. And this structure, kind of in the bottom left, is a fish crib. They'll construct this, put it on a barge, take it offshore, and sink it. Sometimes they could be kind of like an offshore breaker kind of thing, but especially a fish crib. So here we're in the middle of the country, away from any coastal stuff, and we've got a company dealing with coastal dynamics. Kind of interesting. So that's it for today on flooding and coastal areas, and we'll see you next time.